All right, so I just gave back some homeworks. A little late this year, had a little unscheduled situation, so we got a little bit behind. So unfortunately, this week is going to be a little compressed. Floating point representation is going to be on the final. There's a really important IEEE floating point standard that we need to be aware of. All computer scientists should know how floating point works. All right, so today we're going to do Mips Computer Organization. What we saw in previous lecture was how the assembly language statements work and how they're encoded. And now we're going to take a look at the actual CPU of the Mips. And this is, I think this is really a great compare and contrast. This is going to be really nice. So the topic here is Mips Computer Organization. Now, before we actually take a look at the picture of the Mips CPU organization, let's summarize. It's divided into 5 parts, five distinct parts. There is the instruction fetch part, which is abbreviated IF. There is the instruction decode / register file read part, which is abbreviated ID. There is the execute / address calculation, which is the EX, abbreviated EX. There is the memory access, which is abbreviated MEM, and then there is the write back stage, which is abbreviated WB. Now, this nomenclature is standard MIPS. Okay, it's kind of important that because we're using PEP9 and I have modified some of the documentation to be consistent with PEP9, but it's important for you to, probably important for you to know, if, in case you ever deal with MIPS, what is non-standard and what is standard. I'm saying this is kind of like the standard MIPS terminology. Okay, are you guys ready for this? Big drum roll. Here comes the MIPS CPU. Boom, there it is, figure 12.40. All right. Now let's just take a look at this figure 12.40, which is the organization of the Mips CPU. First of all, let's just take a look right in the middle. Do you see in the ID section, what is that shaded part right in the middle that has the C coming in, the A coming in, the B coming in, and the A bus and the B bus coming out, and the C bus going in? That is, what does it say there? That is the register bank. Now that is just like the register bank of the PEP9 CPU. Only difference is we saw the registers, right? Do you remember how many registers there are in MIPS? 32. And do you remember how many bits each register contains? 32. So it's a 4-byte. 4 times 8 is 32. It's a 4-byte wide. Now there is a 64-bit version of MIPS, in which case there's still 32 registers, but each one of them is 64 bits wide. Are you with me? But we're just looking at the 32-bit version of MIPS. Now look, you guys. So there's that register bank. That's at the heart of the whole thing, just like our register bank in PEP9. And look, what does it have coming out of it? An A bus and a B bus. Just like our A bus and a B bus. So it has a 2 output port, register bank. And what does it have coming in up from the bottom? The C bus. Are you with me? Now, I hasten to add that the A bus and the B bus and the C bus are not standard MIPS terminology. But it's just like, but it is the A bus, the B bus, and the C bus. It's just like PEP9. In that respect, it's just almost the spitting image of PEP9. Are you with me? And so, only difference is the A bus, and the B bus, and the C bus all have, how many bits do you think are in those lines? Yeah, 32. Each one of those is a 32-bit line. That represents 32 bits. Is everybody clear on that? I didn't draw them as pipes, like, you know, thick pipes like that, because it would take up too much room. Is everybody clear on that? And furthermore, do you remember in PEP9, how did we access those? We had an A and a B and a C. Well, look, in the register bank, how do we access them? We have what? A, B, and C. And each one of those is how many lines? The A line coming into the register bank, and the B line, how many lines? Right, 5, yeah? And why is that? Because 2 to the 5 is 32. Are you with me? Is everybody clear? So that part is all just hunky-dory. Where is the program counter? So actually I have one big question. Is the program counter in the register bank, yes or no? And what does it look like over here? You see the program? It's way up in the upper left-hand corner. PC. So now why isn't the program counter in the register bank? Because in PEP 9, how do you increment the program counter? It goes through the ALU. But what is the numero uno design principle for a RISC machine? Every instruction has to execute in what? One cycle. That means that every cycle, the program counter has to be incremented as well as having any other results computed. So the idea then is to have the program counter be outside the register bank and to have an adder. Now do you see where the adder is for the program counter? Where is the adder?
Is it the +4?
Well, there's 2 of them. Yeah, there's now why do you, there is and actually you spotted it correctly. That +4. Why do we have a special purpose adder that whose only function, whose only one goal in life is to add 4 to the input and then send and have the output be that input +4? Why do you suppose that we have a special purpose one to do that?
The instructions are all the same length.
And how many bytes are they?
4 bytes.
They're all 4 bytes. So every time we do the von Neumann cycle, we got to add 4 to the program counter. So look, so that's why that +4. So that's why we have that +4. Now, in addition, now we are going to examine each one of these paths in more detail. But look, can you count actually how many muxes we have? What are they? Can we enumerate them? Yes, there's an AMUX, and that's just like, notice where that AMUX is going into? It's going into the ALU. It's just like our AMUX. There is a CMUX. Is there a CMUX? Oh, right at the very bottom in the right back region, there's a CMUX. And notice that that's the CMUX that tells, what to send back up into the, are you with me? Up into the register bank. And there is a PCMUX, and there is a JMUX. So AMUX, CMUX, so are there 4? I think there's 4. So actually they're all listed here. Oh, and by the way, so the JMUX control, PCMUX control, AMUX control, and CMUX control. And now here's another thing, you guys. This terminology is not standard MIPS terminology. But this is the way we're used to seeing our PEP 9 CPU organized. So we're going to use the similar terminology. And also, it's not necessarily the case that that MIPS uses the same. I mean, I'm sure it doesn't. It would be a super coincidence if it did. But what was our convention for MUX control? If it's 0 means the left input goes to the output. 1 to the MUX control means the right input goes to the output. And so we're just going to maintain that convention just to make it easy for us to remember. And it's probably not like that. Chances are 1 out of 16. And therefore, we have a 1 in 16 chance that this is the way it is in the real MIPS machine, so probably not. But anyway, we're just going to use this as our convention because that's what we're used to with PEP 9. All right? And now, what about the, now it's not shown here, but what do you suppose about the ALU? What control, what in the PEP 9 setup, what did we have with the ALU? How did we control the ALU? Do you remember how we controlled the ALU? There's like, how many lines, do you remember?
16.
Well, it could do 16 things, but there were like 4 control lines. Okay, it's the same way with this ALU, but so it's a multi-line, so the ALU control is a multi-line function select. Wait, you know, I said it was, I'm not sure now if it's 16 functions or if it's 32. Maybe I should look that up. Mips ALU. You know, the ALU that we did in the lab was a 16 function ALU, that 7400 series part. But I'm not sure how many functions there are in the Mips ALU. And now the next question is, how many clocks? What is this in the mem access, in the mem section? What is that box? What is that box labeled there on the bottom in the memory access section? Yes, that's an L1 cache. Are you with me? And do you remember what the L1 caches were? Were they unified or split? Do you remember if they were unified? What does a unified mean and what does split mean? Split means there's a cache for what and a cache for what? For the what and the data? Well, for the instructions. A split cache is where there is a separate cache for the instructions as well as, and then a separate one for the data. Well, in a unified cache, they're all together. But in a split cache, you have one cache that's only for instructions and another cache that's only for data. So what we have in the memory access section is the L1 data cache. Whereas, but now where's the instruction cache? That's in what section? Instruction fetch. Yes, that's in the IF section. So that is an instruction cache, right? And now look, what feeds into the instruction cache? What is that arrow coming down from into the instruction cache? What is that? Which register? That's the what? That's the program counter. No. In the PEP9 organization, how did we read something from memory? What did we have to do? When we fetched an instruction, what did we have to do? We had to load the MAR. So what do you suppose that PC is? That PC is basically the what? It's basically the MAR for the what? Instruction cache. Do you see? Are you with me on this? So here, let's write that out, actually. The PC is the, quote, memory address register for the L1 instruction cache. Do you see what we're saying? So what happens is, whatever is in the program counter, that's like the memory address register for the L1 cache. And so what comes out? What is the output of the instruction cache? It's the instruction that's stored in the instruction cache. And what is the MAR of the data cache? What's the address of the data cache? Where is that coming from? That's coming from the ALU. So what else can we say? The program counter is the MAR for the L1 instruction cache. The what is the what for the what? The ALU output is the what? Quote, memory address register of the what? Of the L1 data cache. Is everybody clear on this? So whenever you want to fetch something from memory, what do? You calculate the address of where you want to fetch it from, and then the output of the ALU goes in, feeds into the L1 data cache, and then what comes out of the L1 data cache? The data at that address. Does everybody see how that works? And then there is another really clever thing. If you want to do a computation, but you don't want to compute an address, then what can you do? This is very clever. What do we see in the MEM section and the WB and the write back section? It's possible to take the output of the ALU and go what? Go where? Yeah, bypass the data cache, go straight through the CMUX, and then go back into the register bank. So that path is the path that's taken whenever you want to do like a register-to-register computation, Whereas the other path, the path from the ALU into the register bank, that is the path that you would take when you want to compute an address. Now, in what instructions do you have to compute an address? A load instruction. What would a load instruction do? To do a load, we have to do what? Yes, that's a good answer, because you have to load, so you calculate the address of where to do the load from. The data comes out of the L1 data cache, it goes through the CMUX, and then it goes into the register bank through the CBus. All right, so now let's get back to our original question. How many clocks are there? How many registers here do we have to clock? What parts are sequential? What can we clock things into? Yes, the data cache. If you want to clock something into memory, there is a clock input to the data cache. That's one. That's very good. Well, now that's interesting. For the instruction cache, basically what we're going to do is the program counter is going to request something from that from the instruction cache, and every cycle there's either going to be a hit or a miss. So that's kind of like automatic. So
Program counter.
aha, the program counter. So yeah, so the program counter will be, we need to clock that in every cycle. And what else? There's one more big important one.
The register bank?
Yeah, the register bank, because you know whatever's in the C, so you put whatever is on the C bus, and then C comes down from the decode instruction part, and so we need to, and so there's going to be a load CK. Right, so there's going to be those three. So here, that's on this slide. All right. So the PC CK, that's the clock pulse for the program counter. The load CK, that's the clock pulse for the write to register bank. And the DC CK is the clock pulse for the L1 data cache. So those are, and the instruction cache, that happens more or less automatically, so we're not going to consider that one. Now you guys, check this out. Here in figure 12.40 is how the data flows. Now in PEP 9, where did all those control signals come from? In PEP 9, which was micro-coded, where did all those signals come from? I mean, just on the figure. Yeah, they came from the left side, and they boom went in there, and then we saw later that, you know, how there was like a micro instruction register and a micro program counter and a, you know, and how all those things got generated by microcode. But with MIPS, there is no microcode. Where do you suppose these control signals come from? Here in figure 12.40, where do you suppose those control signals come from? There is no like control section over here that does lots of cycles per instruction. So where do you suppose those control signals come from? It's here on the figure 12.40 somewhere. Where are they? Where do you suppose there's a block in here where those control signals come from? Can you imagine which block? One of these blocks.
It's going to come from like the decoder?
It's going to come from the, that is absolutely right. It is going to come from the decode instruction unit. So look, here's a picture. Figure 12.41. It gets messy to show every control signal and every data flow signal, so I just erased some of the data flow signals. But look, it comes from that decode instruction section. And where does it go? It goes to each one of the muxes. A line goes to the A mux, a line goes to the C mux. What were the other muxes? A line goes to the PC mux, and a line goes to the J mux. Are you with me? And then the clock pulses, a line goes to the PC CK, PC clock, a line goes to the load clock, and a line goes to the, we call it DC CK, data cache clock. That's DC CK is the data cache clock. And that's the origin of it. And you guys look, that box in the decode, what kind of a circuit is it? Combinational or sequential? What kind of a circuit is it? Is it combinational or sequential? Does the output depend only on the input for that? For this decode instructions, does the output depend only on the input? Yes or no? This is tricky. But conceptually, does the output depend only on, what is the input coming from? The input is coming from, no, where is the input coming from of the decode? Where's it coming from? The what? Where is the input of the decode instruction coming from? the L1, what? Instruction cache. So what's going into it is an instruction. And what is that what are the parts of the instruction? It has a 6-bit opcode. It has a register field, another register field, and it has an immediate field. Are you with me? So that instruction is going into the decode, and the output depends only on the input. So you should think of it as a combinational circuit. Oh, that's a good question. Oh, that's a good question. So you were thinking about the feedback loop and how it goes, yeah. But look, do you see though that the main feedback thing is with the register bank? When you clock it, because the register bank goes through the A bus and the B bus and possibly goes into the data cache and possibly comes around and goes back into the register bank. So every time so what happens is the instruction that's being executed, the program counter has the address of the instruction that's being executed. Are you with me? And then that's feeding into the instruction cache. And we can think of that after a few gate delays. The instruction at that address is being presented to the decode. And then after a few more gate delays, because it's a combinational circuit, the data is presented on the A bus and the B bus and the C bus to the, sorry, not the A bus, B bus, and the C bus, but the A, B, and C register addresses is being presented to the register bank. Are you with me? And then, so that's being presented to the register bank. And then the register bank, depending on the values of A, B, and C, is sending information, information is being presented down the A bus and the B bus and through the AMUX and the ALU and et cetera, and down, and is also being presented to the register bank, right? And not only that, information about the next value of the program counter is being presented to the input to the program counter. So the program counter has the address of the instruction to be executed next, and the output of the program counter is not the same as the input to the program counter. So in one cycle, now think about what you said. In one cycle, or in one clock pulse, what changes with each clock pulse? The content of what changes with each clock pulse? What's in the data cache? Are you with me? What's in the register bank? Are you with me? And what's in the program counter? But that's all master-slave. So that when that happens in one cycle, because the program counter changes, that might change what's presented to the register bank, but it's master-slave. So it doesn't, that feedback doesn't happen. But the main thing to understand, the main thing to visualize is that the decode instruction box is combinational. The output depends only on the input. Now, here's the thing. Now what we're going to do is we're going to be able to see, or we're going to be able to design some typical, we're going to be able to manipulate these control signals. And what control signals do we have to manipulate? We have JMUX control, PCMUX control, AMUX control, CMUX control. So there's 4. And then there's ALU control, 5, PC clock, 6, load clock, 7, data cache clock, 8. So all we have are just like 8 control signals. We'll be able to specify each one of those to see how each instruction in the MIPS instruction set is implemented. And everything happens in just one cycle. Every instruction happens in one cycle. And that includes updating the program counter. Let's take a look at how the MIPS machine fetches an instruction. So we pointed this out before. The program counter, PC, is not a general register in the register bank. And +4 is a special purpose adder to increment the program counter by 4. An expanded version of figure 12.40. And here you can see the line from the JMUX that goes to the PC. If, like, an instruction executes that's not a branch instruction, then what do we want to do? We want to add 4 to the program counter. So how would we add 4 to the... So let's write down the control signals necessary to add 4 to the program counter. So how would we add 4 to the program counter? The program counter branches off as the input to the what? +4. And so what do we want that plus 4 to, where do we want that plus 4 to go? The output of that plus 4 goes to PC. So what do we have to do? So here let's do to add 4 to the program counter. So what does PC mux have to be? That's right. So PC mux would have to be 0, comma, then what? And J mux would have to be 1. See how this is just like PEP9. And then what? Yeah, PC CK. Yeah. So this has to happen on every, like this has to happen with the other ones. You know, this is just incrementing the program counter by 4. There is a MIPS jump instruction. It uses pseudo-direct addressing with JType. You can go back and look up what the JType instruction is, but this is an interesting little bit of a tricky RTL, Register Transfer Language Specification. And here again, let me hasten to add, I mentioned this once before, but let's say it again. The bit numbering convention is not like MIPS. MIPS is called a little Indian machine. PEP9 is a big Indian machine. We number our bits the same way they're numbered in C. 0 is the least significant. 0, 1, 2, we number them from left to right. This is not MIPS standard terminology. This is not common. I mean, you show this to somebody who knows something about MIPS, they say, what the heck is going on there? Because, you know, just to keep it simple for PEP9, you know, to make it the same as PEP9. So what does this notation tell us? It says, first of all, in the jump instruction, there is a 26-bit unsigned integer. Because instructions are all 4 bytes wide, what do you think the alignment, how do you think all programs have to be aligned in a MIPS program? Remember how we talked about alignment? Well, all instructions are aligned at addresses that are divisible by 4. So it doesn't make any, so therefore the last 2 bits are missing. The 2 least significant address lines are missing because each instruction is always going to be at an address that's aligned by 4. So consequently, a 26-bit unsigned integer in an instruction is assumed to have 2 trailing zeros in that address field. So what the program counter gets is it gets TA, that 26-bit unsigned integer, times 4. Now why times 4? That takes into account the fact that those 2 bits are assumed to be 0. Those 2 least significant bits are assumed to be 0 in the address line, because times 4 is a shift left by 2. Are you with me? And now if you take 26 bits and you shift left by 2, now how many bits do we have? 26, 27, 28. And then how many more do we need to get up to 32? 28, 29, 30, 31, 30. We need 4 more. So what it does is it takes the incremented value of the program counter, PC plus 4, and that 0.3 is the most significant 4 bits, and it concatenates it. That colon is concatenation. It concatenates it with the shifted TA. Now look, and here, look at what it takes to do that. JMUX equals 0, PCCK. Now why in the heck is that? Look. Let's come back to figure 12.40, our expanded version here. So it takes what's in the program counter, right? That goes through the plus 4. And you see the address line, the 26 bits from the address field come off of the instruction. Do you see over here? These 26 lines coming from the address field of the instruction. All right. And then they're going into, what does this ASL2 do? Yeah, arithmetic shift left 2, so that's just a combinational circuit that shifts left 2. So then we have 28 bits coming out there, and then we have those 4 lines coming from the plus 4, and then that horizontal line says they're concatenated, and so all we need to do is set JMUX to 0 so that the JMUX will go through and be clocked into the program counter. And so all of that, because of that specialized hardware, all of that can happen with just JMUX get 0 and PCCK. And this next slide, oh, we already did this. I should have put these slides in the opposite order. Next instruction, non-branch instructions, or conditional branch instructions when the branch is not taken. So PCMux and JMux route PC plus 4 to the program counter as the address of the next instruction. So here it is, PCMux gets 0, JMux gets 1, PC clock. Yeah, so we already have done this one. Did I mention this before? The MIPS has no status bits? Yeah, MIPS has no NZVC status bits. Comparison is always between two registers, and so you have add. If you execute the add instruction, if there is an overflow when it's considered as signed, then it triggers a trap, a system trap. And add U for add unsigned does not. Here are the control signals that come out of the decoder when a branch instruction is taken. So again, this time IM is a 16-bit unsigned integer. And SE, did we mention what SE is? SE is sign extension. So do you guys know how sign extension works? Like here, if, let me do a small example. So suppose you go from 5-bit to 8-bit sign extension. So here, if the number you have is 0, 1, 0, 1, 1, 1, 2, 3, 4, 5, this is 5 bits. Then how would you sign extend this to 8 bits? Because the sign bit here is 0, that's what you extend. So 1, 2, 3, 4, 5, 6, so it would be like this, 0, 0, 1, 0, 1, 1. So this sign bit gets extended with zeros. But on the other hand, if it's 1, 1, 0, 1, 1, then how does that get extended? 1, 1, 1, 1, 1, 0, 1, 1. Are you with me? So what happens is the sign extension does not change the value. What negative number is this? If this were 1, 2, 3, 4, if this were a 5-bit number and this were the sign bit, what number would this be? -5. And what number would this be?
Same.
Also -5. See? Are you with me? And what number would this be? 0 in the sign bit. So what number would this be? Is that 11? 8 plus 2. Yeah, 11. And what number is this? Also 11. So sign extension doesn't change the value of the number. So, but this is a 16-bit unsigned integer, sign extended. And so it takes PC plus 4 and it sign extends the immediate field times 4. So let's go back and look at this time. Instead of the address going into the ASL2, the address field goes into what? The 16 bits of the address field goes into the what? You see in the ID section. It goes into the sign extend field. That extends it to 32 bits. And then it gets arithmetic shift lefted twice. That's because, same reason as before. And then there is a special purpose adder here, a 32-bit adder, that then goes through the PCMux and the JMux to the PC. So all we have to do is set PCMux to what? To get that into the PC. We set PCMux to what? Can you tell here on figure 1240? 1, and JMux to 1. So is that what it said? Yeah, sure enough. PCMux 1, JMux 1, PCCK. And now, let's just do 2 more. Here's the store instruction. And look, just 1 cycle. What does the store instruction do? Memory to register or register, memory to CPU or CPU to memory? Store is what? CPU to memory. So it takes whatever's in register RT and it sends it to that address in memory. So basically what it is it's a combination of this. Do we have these control signals? PCMux is 0, JMux is 1, and then at the end a PCCK, are you with me? Together with the what? With A equals RT, AMux equals 1, so let's go back and look at that. A is the register in the RT field, and then AMux is 1, B is the base register, ALU gets the function A plus B, and then PCCK and DCCK. So let's go back. So let's trace it through. So this is a store instruction. So we're putting something into the, so the C, so we're not clocking anything back into the register bank. We're clocking it into the data cache, right? So it's the DC clock. The data cache clock is what gets activated, is what gets pulsed. And what is getting pulsed into the data cache? It's that data in. And where does that data in come from? That comes from the A bus. AMUX is 1 because that's the address calculation. So the address calculation is going through the ALU and being presented to the right. The ALU is calculating the address of the data to be stored in the L1 data cache, and the data itself comes from the A bus, and that's being presented to the data in of the L1 data cache. And then there's one more add instruction. Here's the add instruction. I'll let you work through this. But this is the sequence, you know, for the add instruction. But I think once you see the way the data flows, it all makes sense. And it's just like PEP9. Once you've done those microcode stuff, you know, the MUX goes this way and makes it go that. You can see it's a very clever. It's a very nice arrangement of the items in this RISC machine that lets every instruction execute in just one cycle. Very nice design. Very nice, clean design. Okay, good deal. See you next time.